All right, good evening. Today we're going to be going over the 2022 exam. This is our Organic Chemistry 2 final exam review. So one thing about this exam is that thankfully we don't have the worst section. We have no facts section. That's going to be your ACS final review. Fortunately, we can't cover that because I think we'll be able to show that. But we'll go over this exam, and if you guys have any questions, talk. Um, so yeah, so this exam is worth 50% of your grade, and then the ACS exam is worth another 50%, total 100. The ACS exam is pretty much, I would say, it's very similar to the exams that you had, like with Dr. Bean. It's just that now they're multiple choice. So if you guys are too like very worried, think you won't do well, don't be too worried. It's gonna cover everything, OChem 1 and OChem 2. So it might have some questions that you're gonna see in OChem 1 that would be like exam 1 or exam 2 material, and you'll feel comfortable on that, especially if they're multiple choice. And then even OChem 2, you see like multiple choice questions. It makes it a lot easier if you have to. All right, we'll get started now. So first, naming. So over here we have an ester that's also linked to an amine. So in this, the ester is going to be our parent chain. It's going to be our parent group. And we'll start counting from the substituent side. So remember on esters, we have the parent side, which is going to be the side without the oxygen bond. And then the sub side, so sub and parent, right? So we'll start with the sub side to get it out of the way. So we have a 1, 2, and then we have a benzene ring. So that is a 2- phenyl, right? So subs 2 phenyl, and then because it's 2 carbon chain, we're going to call it ethyl. So 2 phenyl ethyl is going to be our sub. And then for the parent chain numbering, we'll start with the carbon that's connected to the ether or the ester. So 1, 2, 3, 4, and 5. And then we have a nitrogen group that's going to be having 2 ethyl groups attached to it. So this is one of the occasions that we're not going to be using N to show that the nitrogen has an that we have a substituent on the nitrogen. So in this case, we're looking at nitrogen as a we're looking at as a substituent, right? So because the nitrogen is a sub, we're not going to be having an N, right? It's not going to be N comma N diethyl because then we don't know where the nitrogen is, right? So we can't put an N diethyl. Instead, what we're going to have to do for that substituent, we're going to put 5 dash um is it- no, yeah, it's just 5 diethyl amino. So amino denotes that we have a nitrogen there, diethyl amino, and that will be our substituent. And then our parent chain will be the pentane, right? Just 5 carbons. But because we have the ester, and our ester is going to be our parent chain, it's going to become pentanoate. So pentanoate. So now if we were to put it all together, we have a we don't have any stereochemistry that we have to worry about, so we can just do the entire thing. So 2-phenyl ethyl. And then remember for esters we leave a space in the middle. So I'll put this put like a dash to show that we have a space there. Phenyl ethyl 5 diethylamino. Pentanoate. Right? So on the exam, I wouldn't recommend putting this squiggly here, but definitely try to leave a space. One other way that you can just show that you left a space is that like you YL. just make sure not to put that dash, because if you put that dash, they're gonna assume that you meant that it was gonna be in the same word. So because we have no dash there, it's easy to it's easy to tell that it's not gonna be that it's gonna be a space and not part of the same word, right? So, are there any questions on that? Yeah. Yeah, OATE. Any other questions? All right. So we'll go to the next one. So this one we have a alkene with nitrogen bonding. So over here, this is actually one of the cases because the nitrogen is going to be part of our parent chain that we're going to be using N comma N, right? Because we have two substituents here. So this is where we would be using NN, right? The other one, because the nitrogen wasn't part of the parent chain, we called it a diethylamino, and that was the entire. This diethylamino is essentially just saying we have 5 diethylamino, like that, right? We're including the nitrogen in that substituent, right? But for this one, because nitrogen is part of the parent chain, we're gonna denominate that whenever we're putting the substituent number as n instead of 5. So to do this, we'll start by numbering the parent chain. So we're gonna start with the longest chain, or the chain that has the most double or triple bonds. So we see on the left we have a double bond, so we'll number towards that side. 1, 2, 3, 4, 5, and 6. So there's no other way to number it because we're starting from the nitrogen as our parent. So that would be it. Now if we look at the substituents, so subs, on 4 we have a methyl. And now we have 2 groups right here on the nitrogen. And so these groups are going to be 1, 2, 3 carbons long, 1, 2, 3 carbons long. So they're both propyl groups. So what we would put here as the subs, we would put N comma N dipropyl. And then okay, and N dipropyl. Give me 1 second. Let me turn off this low power mode. Getting really dark on me. My bad, guys. All right. So NN dipropyl, and then that will be our substituent naming. And now for our parent chain, we have a 6-carbon chain, so hexene. And remember, we have to denote where the double bond is. So we'll put 5-hexene, right? And then we also have to show that it's an amine as part of the parent chain. So that's going to be 5-hexene, and then we'll add amine at the end, right? So that'll be it. I think you don't have to, but I think you can put 1 here. So hexene 1 dash amine. I think that's fine if you don't put that, because it's already assumed that the amine is on 1. If you want to stay safe, then I would suggest doing that. Anyway, to put it all together, so we'll start with the alphabetical order. So M comes before P, right? We're not going to be using the di because it's just denoting how many of the propyls that we have. So we'll start 4-methyl dash N comma N dipropyl dash 5 dash hexene dash 1 dash amine. And then also you can put dipropyl X dash 5 dash ene amine. You can put 1 in between there as well, right? So there are a lot of ways that you can write this out. All of them would be correct if you found a different way. Yeah. They're all good. So in this one, we won't use 5,5-diethyl because the way that the amino works, we're not showing that we have two amine groups, right? We have one nitrogen, so we're only gonna put one number there. That makes sense. Yeah. Yeah. One more time. And then dipropyl. I don't know why. Yeah, I don't know why. Yeah, sorry. Okay. Yeah. Yeah, you had a question? Yeah, my bad. Uh, okay. No more questions? Okay. So, third one. Um, maybe it is NN. I'm not sure. And I thought it was just from alphabetical order. That's here. We'll put an asterisk here. And I'll get back to you on that because I'm not sure. Okay. So third one. So we have an aldehyde, we have a ketone, and we have an ether. So all of these are potential parent chains, but remember, it goes from ether being the lowest, then ketone, and then aldehyde. So our aldehyde is going to be our parent chain um in this one because the aldehydes have higher priority than ketones. So we'll start numbering from the aldehyde carbon. 1, 2, 3, 4, 5, 6, 7. So 7 carbon chain. And then we'll start naming the substituents. So subs on carbon 6, we have an oxo group. So our ketones, we called oxos. And then on carbon 4, we have an ethyl group attached to the ether. So this is going to be a 4 dash ethoxy, right? So now that we've done that, we can start naming the parent chain. Seems so short, but so the parent chain is going to be a 7 carbon chain, so heptane, right? Heptane, and then because we have the aldehyde, whenever aldehyde is the parent chain, we drop the E and add Al, so heptanal, right? And we don't have to show that it's going to be a 1 dash heptanal because it's already assumed. So don't worry about that. So heptanal is fine. And now we have some stereochemistry. So we have a chiral carbon right here, right? And so now we have to look at the biggest groups and the smallest groups. So immediately this hydrogen is going to be our smallest group and this oxygen is going to be our biggest group, right? Because we have 2 carbons right here on either side. So we'll start going through the carbons. So uh so between carbon 5 and carbon 3, carbon 5 has 1 carbon attachment and 2 hydrogen attachments. And then carbon 3 has the same thing. So we'll go to the next carbon. So carbons 2 and carbon 6. So carbon 6 has 2 oxygen attachments and 1 carbon attachment. And then carbon 2 has 1 carbon and 2 hydrogens. So because of that, the group on the left, the 4, 5, 6, 7, is going to be bigger than the group on the right. So we'll name that 2 and then 3. And then we make an arrow from 1 to 2 to 3. And this is counterclockwise. Counterclockwise. And so counterclockwise. Yeah, counterclockwise is going to be S, right? And because the groups are on the right wedges and dashes, we're not going to switch it over to R. So it's going to stay to S. So S is going to be our stereo. And we don't have any double bond stereochemistry, so we can just start naming. So we'll start S dash, and then we'll start with the ethoxy. So S dash 4 dash ethoxy dash 6 dash oxoheptanal. And that will be our IUPAC name. Any questions on this problem? No questions. Okay, so we skipped the facts section and now we are at reactions. So one thing to note about the reaction section is that you'll have reactions from all of OChem. So you'll have SN1, SN2 reactions, you might have E2 reactions. So you have reactions from everywhere, all throughout OChem 1 and OChem 2, all of them are fair game. So please be careful. You know, maybe you'll see something that you don't recognize, but it'll be a reaction that you know, right? Maybe you'll see like you might see like T-butoxide, maybe you forgot, right? And then you forget that it's a bulky base that does SN2 or E2, sorry. And it's very easy to make small mistakes on this section. So please be careful, right? Just a word. So MCPBA, first step. So we have an alkene, right? Alkenes with MCPBA create epoxides, right? So we'll start by making an epoxide. So our first step is we'll create that epoxide. We have our methyl group. I'll put our methyl group on a wedge or on a dash, sorry, and then our epoxide on a wedge. So we have our epoxides on the wedge. Now we go CH3OH and H plus. This is an acidic reaction, right? And so whenever we have an acidic reaction, we know that this base or this acid attacks the most sub side, right? So it'll attack the most sub side as like an SN2 reaction, and then it'll break off that bond with the oxygen, and this H plus will go and protonate this O minus back up, right, to an OH. So what that'll look like in the second step is that we'll have our SN2 reaction that takes place, right? So now the methyl is on a wedge and the OCH3, remember we're adding this group right here. So the OCH3 is on a dash, and then the other side, the OH is still on a wedge, right? And now our third step, we have sodium dichromate, right? This is a strong oxidizing group, strong ox. And so what that'll do, it won't do anything to the ether, but to the alcohol, it'll oxidize it as much as it can. So because we have a secondary alcohol, it can't go past the ketone stage. So it's going to go all the way to the ketone and then stop there, right? So we won't be able to make carboxylic acids or esters or anything, but we'll make ketones from that secondary alcohol. If we had a primary alcohol, it would make the carboxylic acid, right? So the step for this, we still have the same OCH3, and now we have a ketone. Very simple. And now we have our Wittig reaction. And so what that's going to do, what I like to think of this as is just the one that replaces the oxygen. So instead of this P trying to complicate things in that big group right there, I just put an oxygen right here, and I just pretend that this is the oxygen goes and kind of just leaves, and that double bond to this oxygen is now a double bond to that carbon. So this is going to be our final step. So the methyl group, OCH3, and then this double bond, right? No longer connected to the oxygen, but now connected to the carbon. So it's carbon, and it has two methyl groups attached to it. So CH3, CH3. And that'll be the answer to the first reaction question. Anything you guys have? I think pretty simple, right? So this is like mainly OChem 1 stuff, right? So there's a little bit of ease in some of these questions, right? So the second question, so it might be hard to tell. I think whenever I was studying for the exam, it was very hard for me to tell like what kind of reaction with this was. But sometimes it just takes a change of perspective, right? So if we look at it like this, suddenly this becomes a very nice Diels-Alder problem. So we have the aldehyde in heat for step 1, and we have a diene, right? So the result of this, remember in Diels-Alder, we have this bond attacking this part, this attacking this, and then this stabilizing by creating a double bond in the center, right? So what we will have is a cyclohexene ring, and then what we have to do is that we have to put this this group onto a dash, right? Because or onto a wedge, sorry. So this, which is the carbon, and then double bond O, hydrogen, right? So technically it doesn't really mean anything because going on we don't have to worry about stereochemistry in the problem. But I mean it's good to like, keep yourself in practice, I guess. So second step, Ag2O, H2O THF. So this is a reaction probably you guys maybe don't remember. This is Tollen's reagent. So what the Tollen's reagent does is I think it's called a silver mirror, right? Silver mirror. I think you guys may remember doing in your lab. So in this one, the aldehyde goes and becomes a carboxylic acid to carb acid, right? So this aldehyde is going to be a carboxylic acid now. I won't put the wedge here just to keep my sanity. OH. Okay. NH3 and then heat greater than 100 degrees Celsius. So this is the creation of an amide. So we're creating an amide here. Amide, right? So we have the amine that's reacting with the carboxylic acid that creates an amide. So our third step is going to be to change that OH on the carboxylic acid into an NH2. And now we have our final step, Br2 OH in heat. And this is, I forgot what it was called, the Hoffman rearrangement, right? Hoffman rearrangement. So that's just a big word for saying take off the carbonyl. So the final product for this reaction, we're just going to take off this carbonyl and the carbon. So now we just have the NH2 remaining. All right. Any questions on that problem? No questions? Yeah, sure. All right. So number 3. All right. So we have an amide, right? We'll begin with an amide. And then our first step is LiAlH4 and then H2O, right? So whenever we have an amide that is LiAlH4 and then H2O, it's essentially just taking off the carbonyl. So we'll go ahead and do that. So we'll have 1, 2, 3, 4, 5 carbons plus the NH2. So 5 carbons plus the NH2. And this carbonyl is now gone. So don't worry about that. Now CHI3XS and then Ag2O, H2O in heat. So this is a kind of a weird reaction, but just to put it simply, it creates a terminal alkene. So I think the mechanism, it like attaches 3 CH3s onto the nitrogen, if you guys were curious. Attaches like, so it becomes like N, CH3, 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 and the N has a plus charge now because it has the R group, right? And because of that, it just leaves, and then the Ag2, H2O in heat just creates a double bond right over here, right? So that's basically what that reaction is. You don't have to know the mechanism at all. I'm just letting you guys know, just in case you guys were curious. So we have a terminal alkene now. And now we have, I think it's like one of the first reactions we learned, maybe NBS and heat, right? So one thing about NBS and heat, it creates a radical, or an allylic radical. Sorry, I should clarify. So yeah, so CHI is essentially, okay, so this nitrogen that has two hydrogens attached to it, right? So this CH3I, because it's in excess, what happens is that it just constantly attacks that nitrogen, and it creates this middle step, right? This N plus that has three CH3s attached to it. And so you don't have to know this mechanism, but all it essentially does is like an E2 reaction that it creates a double bond. Yeah. So for the third step, it creates an allylic radical. And so to show that, we'll actually, I'll put this a little bit below because you have to draw the. So remember one thing for NBS and light, if you have the radical, please do resonance because you probably will get points off, right? So we have the radical in a allylic position. And now we can show that this radical can stabilize it this way. Remember, whenever we draw radical lines, it's only one side of the arrow, right? So we have this. This is essentially saying that we are creating a double bond right here, and then a radical will go onto that carbon at the very end. Okay, so I think you have to show this part because for radicalization, I'll show you why actually as well. Because okay, so whenever we look at it this way, whenever we have these two products, NBS in 50 degrees Celsius is a very hot reaction, right? And so whenever we have hot reactions, we create alkenes which are more substituted. So if we look at between these two, this first alkene that I draw, if I label this 1 and label this 2, this first alkene that I've drawn, how many substituents does it have? It only has the one substituent right here, right? So one substituent, I guess aptly named. And then number 2 has two substituents, right? So we have two substituents versus one sub, right? And because it creates a more subbed alkene, it's gonna react with this right one, right? So you wouldn't have gotten that this how do you say? Yeah, if you draw, I don't think you, I think you have to show the step to drawing the major though. That's the thing. You don't? Oh, okay. Appreciate it. Sorry. I just assumed because usually what's it? Usually they ask you to put the resonance for all these. Okay, well that's nice then. If you can figure this out, like and get the correct major contributor, then that's perfect. That's yeah, you just have to put this one. Thank you for clarifying. So okay, yeah. So on this one, because number 2 is going to be the one that's going to be attacked by the NBS, is going to add a bromine where that radical would be, right? So we have the bromine there, and now step 4. Step 4, NaN3. This is sodium azide. Yeah, sodium azide. Sodium azide, and it does a little reaction that causes this Br to leave, and it creates an N2 there. So we just did like this. We'll just put N2 minus. You don't have to put the minus in this case, because yeah, you don't have to put the minus because there's no yeah. So this would just be N2, right? And then finally, we have our LiLH4 H2O. And what that's going to do is that's going to not protonate, but it's going to reduce. This is step 5. It's going to reduce this N2 all the way down to an amine. So we have a primary amine, NH2, and I missed the double bond. So just like that. So that will be our answer for number 3. Any questions? No questions? All right. So fourth one, we have an NAS reaction. So NAS. So one thing about NAS reactions is that it reacts whenever we have a halide that is ortho or para to an electron withdrawing group. And we have an electron withdrawing group in the nitrogen, and we have a halide that's ortho or para. So that's perfect. So what we're going to do here is for step 1. So step 1 is actually 2 steps because it's 2 equivalents, right? So the first step of step 1 is going to, we don't have to show both steps. We just have to show like the final product of it. But if, for example, if it says 1 equivalence, then you would have to know what the product would be as well. So if it said 1 equivalence, the first step is that you have this NO2 and it creates an OH, okay? Right? And the second step right here of the first, I guess the second equivalence of the first step is going to take that H away. So it's going to become an O minus, right? So O minus and NO2, right? You can put O minus Na plus. That would be nice. So O minus and NO2, right? And then CH2, CH3Br, that's just classic SN2, right? So step 2, we have our ether that's being created. So OCH2CH3, or we're just adding whatever's right there. And then lastly, we have our Birch reduction. So in the Birch reduction, what we have is we take away one of the double bonds and then we create two parallel double bonds that are not attached to any withdrawing group. Not attached to electron withdrawing group. So that means that we have a correct way to draw those 2 bonds. So if we just drew everything back on, because it doesn't change the substituents on it, CH2, CH3, and O2. If we created something that looked like this would be incorrect because it's connected to an electron withdrawing group, right? So we'll go to the next one. And this one is not connected to any electron withdrawing groups. So this would be our correct answer. Any questions? Yeah. One more time. Mm-hmm. So yeah, if you're asking if it had yeah, let's say I had this OCH2, CH3. It's a good question. NO2 and NO2. Like, is this what you're trying to say? Right? So if you had a Birch reduction here, you wouldn't be able to do anything right here because this would just be not very stable. Well, maybe that would be the answer. If I did it like this, I would say that this would be the correct answer, the most correct answer. Because it's connected to the donating group and it's only connected to one withdrawing group. Yeah. I would say it's the most correct to do it this way. but I think an argument can be made for it to be like, I'll put it in a different color. For it to be like this, because on this side we don't have any electron withdrawing groups, and on this side we only have the one electron withdrawing group, and it's stabilized by this electron donating group. So I think the black might be better, just because I don't know if you can even do this at all, but I think the blue could be possible, but definitely not like this. Definitely not, because you're just touching two electron withdrawing groups. Any other questions? No. Okay, so yeah, that's a good question. So NaOH2 equivalents in 100 degrees Celsius. So we have over here, we have a base, right? And so because of that, or a nucleophile, not a base. So we have a very strong nucleophile, and then we have halides. Usually you don't start with halides unless you're doing NAS, okay? And then another clue that I had was this NO2. It's an electron withdrawing group that's ortho to a halide, right? And so from the beginning, it's just telling me, okay, do NAS, right? Because all the clues are there. Any other question? No? Okay. So this is our last fact question. So this is going to be, it's not aldol, this is Claisen, okay? So NaOET, ETOH. So this tells you it's either aldol or Claisen. Claisen. But whenever we have an ester, it's going to be Claisen, right? Whenever we have a ketone, it's going to be aldol. So we're going to choose Claisen. If it's a ketone like this, or if it's a ketone, then it's going to be aldol. But in this case, we have Claisen. Okay, so our first step in Claisen is to deprotonate the alpha hydrogen. So we have this. So one thing for Claisen in this, because we only have the one ester, it's assumed that whenever we create this negative charge, for the first step, that it attacks itself, right? So in this, we actually have like kind of two reactions. So technically, the NaOT ethanol, it only ever deprotonates, but because we have this minus charge and we have two esters, we would actually make them attack each other, or not each other. We would actually make them attack so that we have a reaction take place, right? So our first step is going to be that reaction. Okay. So I think in this one, let me think. Yeah, I think in this one you do have to draw the um what's it? The resonance. So in this case, we have this, and then this is going over here. So we actually have more resonance structures than this too. Yeah, I think for Claisen, if you don't, I think it's like 1 point off. Yeah, for Claisen. Yeah, I think maybe for Aldol, but I'm not sure. Yeah, I don't make the keys. I just kind of follow them, my fault. But I'm pretty sure this one, you do have to um, put the transition states, not the transition states, the resonance structures. If I'm wrong, please like correct me. O minus, and we have our O. Yeah, that should be fine. So we've created our most stable resonance contributor, right? So from this, now we can just do the reaction. So our step one will be to react the two esters with each other. So, wow, that was bad. Okay, so it's a little bit weird to look at it in a way. So what I like to do is I like to draw the starting molecule. So this one that we have, the exact same way. O minus, because we know that the O bond gets off, so it becomes an O minus. Then dash O this. Then we have our, this is going to be attached right here, and that's this carbon. This carbon has two ends to it, so one end goes immediately to this ester, and then the other end has 1, 2, 3 carbons. So 1, 2, 3 carbons, and then it also is with this minus charge, it has a double bond right here. So yeah. So in this case, we're not going to draw the most stable resonance contributor for this. Instead, we'll just draw the double bond on the oxygen and then have the minus charge right here. Okay. So that's going to be our answer to the first problem for the first step. Right. Second step, we have CH3, CH2, Br. So CH3, CH2, and Br. Is it? Oh, it totally is. You're right. Yeah, okay. Then I was wrong about that. Like many things. O minus right here. Not double bond. Then we have, okay, yeah, then we just have the minus charge right here. So we have two minus charges then. Okay, so second step, I feel like do we have two minus charges? Let me think, sorry. Okay, so this should be fine. Like this, I hope. All right, so next step, CH2, CH3, Br. Over here, we're actually going to be adding the Br into, oh, that's why I put the minus charge in the wrong place. Sorry. The minus charge is going to be over here. Minus charge right there. Right, that's what it was. Okay, so the minus charge is going to be right there. And then this CH3, CH2Br is going to be attacked by that lone pair. And then it's going to create that CH2Br. It's going to create the CH2Br right over there, which is going to attach. So our second step, we have this go like that. This O minus like that. Okay, so that's what we had already. And now we add the CH2, CH3, CH2, CH3 like that. And so then our last step, H3O and 180 degrees Celsius. So this H3O 180 degrees Celsius is going to cleave off the it's going to cause a ketone to form. I did something wrong here. Because there's not supposed to be four oxygens. Where I don't think it does. Into, what do you? Yeah. No, it attacks itself. It attacks itself. Oh, okay. Thank you. So this enolate no longer has that. Oh, yeah, it has a It has a carbon still. Okay, hold up. let's restart here. Not restart, but let's look at this. Let's look at how we did this real quick. Okay. The butyl. How did it do that? I think what happens is this minus charge comes and restabilizes and then kicks off this O right here like that, which is why we have. I think that's why I was thinking we have this double bond right here and nothing on this side. Is that not it? That's correct, right? Okay, yeah, that's why. Yeah, that was it. Okay, so yeah, my bad, guys. All right, so I'll re-say this. Okay, my fault. So whenever it reattacks, whenever it attacks itself, we have the O minus transition state that's going to be connected like something like this, right? However, this O minus is going to come and retake that double bond and kick off this ester bond, right? And so now we have the ketone and the ester, right? And that makes a lot more sense. And now what we have is just H3O 180 degrees Celsius is going to cut off this ester right here, and we have just the ketone remaining. So final step, step 3, we have, let me count the carbons. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 9 carbon chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then on carbon 5, we have our double bond. And on carbon 6, we have 1, 2, like that. All right. So I know I kind of went back on myself a couple times. So if you guys have any questions, please say something so I can. I feel like I ramble a lot, and so if I don't have a question to go off of, I just nothing. Okay. If you guys have any questions like afterwards, like anything comes to mind, please let me know. Okay. So for the mechanism, we have aldol, right? So this is aldol because we have 2 ketones, right? So we'll look at it. NaOET and ethanol. So this is going to take off an alpha hydrogen, and we are trying to create a cyclopentene right there. So my immediate thinking is that we have 2 options, right? We can take off this hydrogen or this hydrogen, right? But we're for mechanism, especially in this exam, try to think like 1 step ahead, right? For example, if we take off this hydrogen right here, we have a minus charge, right? This minus charge is going to want to attack right there, right? And if it attacked right there, it would have a ring closing, but it would be 1, 2, 3 carbons long. And we don't want that. We want a 5 carbon long chain. So because we know we want a 5 carbon long chain, we're going to deprotonate the hydrogen on the right. So that lone pair takes that hydrogen breaks that bond, and now we have the cyclo with the double bond O minus charge. Yeah, it won't form like a ring that has too much steric hindrance. Yeah. Yeah, 5 or 6. So in this case, we have 5, so we're going for the other one, right? So that's one thing for aldol. Just be careful with about just like deprotonating the first hydrogen you see, right? So we have that oxygen, and now our first step is done. So now what we can have is we can have this lone pair attack this double bond, this carbon, sorry. And so what we can do here, actually no, I lied. we do have to do resonance, fortunately. So we have a resonance contributor here. So this comes and stabilizes this and creates an O minus charge. So that is not where the O is supposed to go. Oh, single bond. Right. So this is a resonance, or not. Yeah. So these are both resonance contributors, but we're still going to be using the left one as the reaction. So in this case, the minus charge attacks this carbon, the bond goes up and makes that oxygen into a negative, into having a negative charge. So we'll draw our arrow and we'll draw it out. O, and this is a ring closing. So we'll have our start numbering our carbons 1, 2, 3, 4, and 5. So if we created a ring structure and we started with 3 and 4 because they're over here, 3 and 4. So 2, 1, 5, right? And then on carbon 5, we have the 1, 2, 3 carbon chain. 1, 2, 3. And on carbon 5, we also have an O minus, right? Okay, so the next step that we have to do here is that we can protonate that O minus using ethanol. So ETO-H. This O minus can go and attack that H and break that bond and make an alcohol. So now we have our one, two, three. Yeah. Now we have our alcohol and the ketone. And now, okay. So this is where some people may make a mistake, right? One thing for aldol is that it has a different reaction than E2, right? So I'll explain what I mean by that. So this final step, we are very, like, as you guys can tell, we are very close to the final product. We just have to create this double bond, right? And kick off this OH. So it's very easy just to get this one wrong. So we know that we have to look at this hydrogen, right? It's beside the ketone and we're doing an aldol reaction, right? So whenever we get that out, if we did NaOET and we got that, it's very easy to do this. Oh, and then we have a minus charge right here. OH. It's very easy just to say, okay, it creates this double bond and this OH leaves. But this is actually not the mechanism that occurs, right? It's actually, it has one small extra step. So this mechanism, what we do is that we cause it to enolate. So we cause it to become an enolate, right? So we have our resonance structure, I guess, is right. So O minus OH. And now what we can do is we can use this double bond to create a double, use this, sorry, lone pair to create a double bond on the oxygen. We can move this double bond over onto this side, and now we can show that this OH leaves. And so that will give us our final product of this with the 5 carbon ring double bonded to an O with these groups attached to it and the double bond, right? So that will be our mechanism. Are there any questions on that? Yeah. Uh, you don't, no, in this case, you're not going to protonate the alcohol. Any other questions? Yeah, exactly. Yeah, it's very weird because it's not like it's very similar to an E2 reaction, but the mechanism isn't like an E2 reaction. That makes sense. So it does the same thing, but it's not the same thing. Yeah,
Oh, sorry.
no problem.
In case we want to go back to it and try to study it again, is there an
Online version of the test to access the PDF. I'll have it on the description of the YouTube video. Yeah. So I'll put it there. Otherwise, hold up. Give me 1 second. All right. So synthesis. Sorry, any other questions on the mechanism? Okay. Synthesis. All right. So synthesis, we have a Michael reaction. Uh, so the first thing we want to do whenever we get to Michael is that we skip it. Okay, we don't do Michael. I'm just joking. Okay, so the first thing we want to do whenever we have Michael, we want to look at what the donors and the acceptors are. Donor and acceptor. So whenever we have a donor, I don't have them all memorized, but if we look at this, we have a beta keto ester, right? If we look at it like this, we have a alpha beta keto ester. So beta keto ester. And what we can have is that this beta keto ester creates a bond in the center. And this we would have an enol, right? So that would be our acceptor, the enol. Enol and the donor are beta keto ester. So one thing about Michael is that you always want to figure out where the bond is being created, right? Because the first step for Michael, NaOH or NaOET/ethanol, the first step for Michael is always going to be like that, right? So you just have to figure out that where is the bond being created. And it's very like in this one, it's a little bit easier than other ones to see that the bond is right here based on this carbon and this carbon together, right? It's like the middle ground between the two carbonyls, right? So if we just cleave this, our first step, we'll split them in half. Double bond O, phenol, and then we have two more plus our beta keto ester. All right, so that's our first step, right? So if we go onto the left side, excuse me, excuse me. Oh, my fault. Okay. So next step, so we have to get rid of the double bond in this one. So what we can do is we can use like a very strong base. So one thing I just like to do, I just use TB-toxide, right? So what that does, it just creates the bromine onto wherever I want, because both of them would create the most sub or the same amount of subs. So I don't know why I'm putting the brackets. If I had fluorine, then we had our double bond to the oxygen. I can put my bromine right here, right? And so notice how we have an allylic bromine that's going to be close to the, this is an F, is going to be close to the ketone, right? So one reaction that does this is Br2 and acetic acid. And so what that'll do, the product of this will be our F will have benzene ring attached to it. And then like that. And sorry, I should have gone over. Sorry. We can start from benzene, aniline, or alcohols or 5 carbons or less. Always look at this first. Don't be like me. So benzene, aniline, alcohols. Just a real quick reminder, aniline is this with the NH2, right? And we know what alcohols or 5 carbons or less are, so that's fine. So Br2 and acetic acid. Then the next step, we can do what's it? Forgetting the name, alkylation. So we'd use AlCl3. And what that'll do is that'll make this complete thing an acid halide. So Cl plus, right, plus the fluorine on the benzene ring. So we have the acid halide. I'll start on the left side. So the first step we could do here, so normally we don't have a reaction to get the fluorine directly onto the benzene ring, right? So what we have to do is we have to create a diazonium salt. So the way we can do that is we can use HBF4 and heat. And that creates our diazonium salt exactly where that fluorine was, and 2 minus Cl plus, right? So we have our diazonium salt, and we know how to make our diazonium salt with NaNO2/HCl, right? And that goes all the way back to our beloved aniline, Na2. That is a valid starting material. So we'll yeah, N2Cl. Yeah. Let me make that a little bit clearer. Uh, I don't think so. Actually, it's better if you do. Anyway, not plus. I'm not sure about the charges if you have to write them. I think it'd be better too. But, NH2, right? That's our aniline starting material. And so we have the acid halide. And so what we can do here, SOCl2, and now we are back to a carboxylic acid, H. So carboxylic acid, and now we can use Jones or sodium dichromate. So Jones or Na2Cr2O7, both of those are fine. And that, what we can do is we can just create the alcohol, primary alcohol that has 1, 2, 3, 4, 5 carbons. 2, 3, 4, 5. Yep. So this is a valid starting material. Alcohols of 5 carbons or less. And now we have this ester on the right side, or this beta keto ester. So remember, whenever we're making a beta keto ester, it's going to be Claisen, right? So in this one, we did Claisen, NaOET/ETOH. The easiest thing I would say to look for this is look at the side of the ketone, right? So just look at the ketone side. So this ketone side has 1, 2 carbons on it, right? So whenever we have Claisen, usually we'll have something that attacks itself, and then it'll have so sorry, let me try to explain it after I draw this. So when this reaction will look like this, right? And so notice how we have like the ketone on one side and the ester on the other, right? And then we can see that whenever we have this deprotonated, right, this is going to, let's say we have another one, it goes and attacks this carbonyl group, right, or the carbon. And if it did attack that carbon, it would get like another group onto here, and then it would have the double bond O, and then it would have the ester linkage, right? And then this would be connected to an ester, versus this one would be cut off. And notice how we have the exact same thing that we have in the other molecule, right? So, and then also, I guess I don't exactly know how to say, but you see how on the left side of this ester, we have 1 and 2 carbons. Then on this side of the ketone, we also have 1 and 2 carbons. That's kind of a clue that we're going to be doing intramolecular um, um, intramolecular Claisen, right? So essentially, what I'm just doing is I'm taking away that beta keto ester and creating an ester using Claisen. Okay. And so we can do now, very simple, we can use Fischer esterification, H plus. Remember, for Fischer esterification, you do have to put the H plus over the arrow. And then this is going to be CH2, CH3, and that CH2, CH3 is going to be connected to an alcohol. So we have an alcohol that's 2 carbons long. That's perfect. So that's one of our starting materials, plus the carboxylic acid. So carboxylic acid, and then we can just use Jones or sodium dichromate again. Jones, and then we have our 1, 2, 3 carbon alcohol. OH 1, 2, 3. Right. And that is our synthesis complete. I didn't explain the Claisen really well, so if you guys have any questions on that, please say something. Yes. Right here. This is where you want? Yeah. Anyone else? Yeah. One more time? Okay, so it would be this this one that has a minus charge. Is that what you're trying to say? Right? Mm-hmm. Yes, this part is Claisen. Yeah, exactly. So this, yeah, essentially this is the bond that's forming right there. Well, not cleaves, but that's the bond that's, yeah, pretty much you need to know it cleaves there, like for the synthesis. But whenever you're having Claisen, it's going to be the bond between the beta keto ester that's formed, right? So like even if we look at up here, so we look at this, we have a beta keto ester. So you see 1 carbon, alpha, and then beta. We have our beta keto ester, right? And so between the alpha and beta is where we created that bond. So if I look over here, we have the alpha and beta position between those, we're creating that bond, right? Yeah. So for Claisen, yeah, it's gonna be a tail cell, right? You have the alpha beta keto and then ketone, and then in between that is gonna be where the bond is formed. That's a lot easier to explain it that way. Thank you for that question. Any other questions? All right. So we'll get to the best part, synthesis. Not synthesis, spectroscopy. Okay. So a compound with the formula C7H12O3 exhibits the IR, H NMR, and carbon-13 NMR spectra shown below. Please identify this compound and draw the structure in the box provided. Okay, so the first thing we do unsaturation number. Remember, 2C plus 2 minus H plus nitrogens, all divided by 2, right? So we have 14 plus 2 minus 12, all divided by 2, which comes out to 2 as an unsaturation number. So what that tells us is that we have either 2 double bonds or we have 1 triple bond. Okay, so 2 unsaturations is just telling us how many extra bonds that we would have rather than hydrogen. So that unsaturation number of 2 says we have 2 double bonds, or the triple bond. Okay, so going on, we have the C7H12O3. So we have 3 oxygens to work with. So we'll try to keep that in mind as we go through this problem. So I usually skip the spectroscopy because, I mean, usually it's not helpful unless you have like that OH peak, or at least in my opinion, right? Okay, so we'll start with the proton NMR. We have a CH3 that's bonded to CH2, right? So we'll look at it like that. Then we have another CH3 that's bonded to a CH2. And so one thing that this tells me, oh, okay, I did not mean, I should not have done that. Okay. One thing that this tells me is that we have 2 different CH3s. And with the way I understand that, the way I can tell is because these CH3s are separate. If there would be the same CH3s, it would say 6H, right? And it would have the 1 peak, right? Or it would even just show 3H, and then we wouldn't have enough hydrogens. So there's 2 ways to tell if you have um, identical carbons, right? Or 3 ways, I guess. So one way, carbon 13 NMR, right? You can count how many peaks there are. In this case, we have 7 peaks, so we have 7 different carbons. And then also you can look from over here. So if you count all of these hydrogens up, they'll come out to 12, right? So we have 2, 4, 6, and then 9, 12. So we have 12 hydrogens. If we had any identicals, maybe it would come out to 6, and then we would multiply it by 2 to get 12 hydrogens, right? So it's essentially saying if we have 6, then we can pretty much mirror it, right? If we had 6 hydrogens here. But because we have all 12 hydrogens, that's telling me that both of these CH3s are different methyl groups, right? So keep going. And also, sorry, and this CH3 is slightly deshielded, so maybe it's close to an oxygen somewhere off, right? So going on, we have a CH2, right? So CH2 that's bonded to a CH3, and this is very deshielded. So maybe this is bonded to an oxygen, or maybe it's bonded to a carbon that has a double bond to an oxygen. So we don't know if it's like this or it's like this yet. Yeah. So, okay, yeah, that's a great question. So usually the normal range for like these carbons are going to be between like 1 and 1.5, right? So whenever we have something like 2 or like further down, even like at 1.5, it's like slightly deshielded, right? But usually you'll see these ppms at like between 0 to 1.5, right? If they weren't deshielded. Yeah. Yeah, we can do that as well. I would say just like we finish the proton NMR, and then we can even go to the carbon 13 to see like what groups we have so that we know what we're working with, right? So if we just keep going, like we don't have all the puzzle pieces yet. So like let's try to get all the puzzle pieces, right? So we have this another CH2, and this CH2 um is going to be attached to a carbon, right? It's attached to a carbon because it has a carbon with no hydrogen. Sorry, this carbon has no hydrogens. And because it's very deshielded, this is like even more deshielded than the other side. It could even be connected to an oxygen right here, right? So perhaps, or maybe even this carbon, it has a double bond to an oxygen. So we have many different ways of interpreting this kind of stuff, right? So we just want to keep our options open, right? So lastly, we have this CH2 that's bonded to CH3, and this is very deshielded. And so because of how like deshielded this is, I know that this could be C to an O, because there's no way it would be past all of this if it was just like deshielded like that. So I can tell straight off the bat this is connected to an oxygen straight like just completely like that, right? So now we know that we don't have any alkene bonds, right? So there's no alkene bonds, so we can scratch that off the list. And so now what we have is that we have an unsaturation number of 2, and we have 2 potential double bonds, right? So we don't have to worry about that dash O, because now we found the rest of our unsaturation right there, right? So the unsaturation one could be right here, and the second unsaturation right there. Okay. So we've taken care of all the unsaturation, and we've taken care of all the oxygens. Now let's see how the oxygens are made, right? So for example, one thing I like to look at, the carbon-13, we see something very far off. If we look at the carbon-13 down here, something that far off, aldehydes or ketones, 182 to 215, and that's past 182 and before 215. So it's in the range. So we have a ketone, right? And then let's see this one as well, 160. It's around 160, right? Yeah, like 165. So if we have carboxylic acids and esters, it's from 160 to 185, right? So between these two, we have 160 to 185. This is a carboxylic acid, or an ester, sorry, because we do not have the OH peak, so it can't be a carboxylic acid, so it'd be an ester, right? If we had a carboxylic acid, we'd probably see something like this over here on the spectroscopy, but we don't, right? So we know that we have one ketone, one ester, and that ester is going to have this OCH2CH3 100%, because that's going to be what the ester is attached to. So in the box, we'll put the CH3, CH2O. So that's 100%. And then we can even go as far as putting this, because we know we have an ester, right? That's the only way we have it. It's not an ether, so, and it's not going to be connected on the ketone side, so it's an ester, right? So as of right now, we've attributed 3 carbons so far, right? But if we look at this side, this carbon, sorry, I should specify, this carbon right here is attached to something that's doesn't have any carbons, right? And so what that can be, no, sorry, I'm looking at the wrong one. Let me see. This CH2 bonded to, yeah, okay, wait, that's what it is. So this CH2 on either side of it is bonded to no hydrogens, right? So no hydrogens here and no hydrogens here. And we know if we have a ketone and an ester, they're probably, according to this exam, is going to be a beta keto ester, right? So this CH2 is telling us that this is the CH2 in between the two carbonyl groups, right? So if we were to draw the ketone like that, that's this CH2 right here, right? And now continue going onto the other side as we go less downfield. Notice how this CH2 with with the 4 peaks, it's bonded to something that's very deshielded. So this carbon right here, right? And so, sorry, I'm trying to explain it, but my mouth is so dry. This CH2 is bonded to a carbon with no hydrogens onto it and a CH3, right? So that kind of makes sense to be our carbons on this side. And if we look back at this, even this CH3, CH2, that's going to be more deshielded. It's probably the one that's attached to the O, right? It's talking about this CH3, right? Versus this CH3, CH2 is probably talking about this CH3 right here, which has the CH2 and then the C in between that ketone, between it and the ketone. And then we could even go a step further. We look at this CH2. Like if we compare this CH2 to the next one, right? We know that this one is going to be closer to the ketone and not in between the two carbonyl groups, because that CH2 is so far downfield that there's no way it's not like that close to an electron withdrawing groups. And so the only way it can be doing like that is that if it was close to two of them, right? So this CH2 was at 2.5 with only one carbonyl beside it, while this one was even further, so we can say that it was close to two carbonyls. So that adds up. And then the last one, there's no way that this CH2 is more deshielded than the carbon that than the hydrogens that are attached to the two carbonyls, unless it was attached to an oxygen. So that's why we have that. And if we look at this, considered both of our um, unsaturation numbers. So we have two unsaturations, and then if we count carbons, 1, 2, 3, 4, 5, 6, and 7 carbons. Any questions on that? No. If you had any questions on the explanation? I feel like I was rambling. No questions? Okay. You guys have anything? Please come up. Otherwise, good luck on your exams, and I hope you guys do well.